Hello and welcome to this presentation on fast fundamental frequency estimation using least squares. This presentation here is based on an ICAS presentation I gave about a year ago, and it's a joint work between me and Tobias Lindstrøm Jensen, Jesper Jensen, Mads Græsbøl Christensen, and Søren Holt Jensen. And we are all from Aalborg University here in Denmark. So, what we are going to look at today is signals that look like what we have in this figure here. So if you look closely, you can see that the signal sort of repeats itself. So if we take a look at the signal at this point in time and at this point in time, then they basically behave in the same way. And a signal that behaves like that is what we call a periodic signal. And mathematically, we can write it in the following way, so the way we have it in 1. So if we shift the signal by tau here, then the signal is equal to itself. And tau here cannot be just any number, it must be the right number, which we call the period of the signal. And tau is equal to 2 pi divided by omega 0, where omega 0 is what we know, or what we call the fundamental frequency. And the talk here today is really about when we get a signal like this, how can we then estimate the delay tau here, or equivalently the fundamental frequency omega 0. So why is this important? Well, we encounter these periodic signals in a lot of applications, and often we would like to find the fundamental frequency of this periodic signal since it conveys some information. So here I've listed a number of applications. So it could be voice, speech, or singing. So we want to know if people are singing on key, for example, in a karaoke system. Or you might want to diagnose, you want to figure out whether people have the Parkinson's disease or not from the voice. This is actually a research project that we are running in the group at the moment. If you also encounter periodic signals when you analyze signals from musical instruments. So I've listed a number of instruments here, and an obvious application is, of course, if you want to tune them, but also if you want to transcribe music automatically. Also, if we go and look at biological signals, such as, for example, the heart rate, the electrocardiographic signal, then we also find periodic signals. So if you want to find or measure your heart rate or the heart rate variability, or you want to look for heart defects, then you also need to analyze periodic signals. And also if you look at rotating machines, there you will also encounter periodic signals, and you can use that for vibration analysis or for estimating the rotation speed. So you can see here we have a lot of different fields where we encounter periodic signals, and you will also encounter a lot of methods for estimating this fundamental frequency in these fields. I'd say in the speech and audio community we have fairly advanced methods, but for example here in sound and vibration, the methods are not so advanced, and it really makes a difference how good an estimator we use for estimating this fundamental frequency. And I'll give you a short example here. So this is from sound and vibration. So you have a tachometer signal here. So imagine that you have some kind of engine which is rotating, and then for every revolution of the engine you will get a pulse like this. And of course, if you can find the fundamental frequency of the signal, then you know the speed of the engine. So how could this be done? Well, according to this book here, which is fairly recent, the way you do it is that you have some kind of trigger level, and then every time you pass this trigger level, then you simply measure the time since the last time it's past this trigger level here. And then to make it robust, we have some kind of hold of time, and we can also have some kind of hysteresis here. But well, this might work okay for a signal like the one we had here, so with a 40 dB SNR. But if we go to a more challenging case, as the one we have here, where we have a 0 dB SNR, this approach here completely breaks down. But the good news is that if we use a bit more sophisticated methods, we can do a lot better. And here is really how good we can do it. So the blue line you see here is the asymptotic femoral low bound. So this is sort of the best thing you can do. And you can see here that even for 0 dB SNR, we could actually estimate the rotation speed of the engine to within an accuracy of 2.5 rounds per minute. So for this signal here, we could estimate, if we had a good enough estimator, we could get this accuracy described here. And the red and the orange curves here are the least squares estimators for different additive noise realizations here. So for Gaussian noise and for Laplacian noise. And you can see that we basically get down to the bound here. So it is in fact possible to accurately estimate the rotation speed of an engine from a noisy signal like this. But in the rest of this presentation here, I will go through how this is done. And first I will give a bit of background about how fundamental frequency estimation is done. So I'll talk about the odds correlation method and the comp filtering methods. They are very common, especially in speech processing. Then I'll talk about the nonlinear least squares estimator and the harmonic summation method. They are very closely related, these two. And finally, I'll give a comparison of all these methods. Then I will talk about our contribution here, which is fast nonlinear least squares estimation. And finally, I will give some results and summarize. But let's start with the background about different fundamental frequency estimation methods. We'll start with the odds correlation method. So you might remember from the first slide that I showed a picture there of a periodic signal, and there a periodic signal would satisfy that if we shift it by some period here time, also some time here tau, then it should be equal to itself. So that means that if we subtract the two from each other, the error here should be 0. In practice, we don't know this tau here, so we have to try out different taus and then find the one that will sort of satisfy this equation 2 up here. Real-world signals, they are not perfectly periodic, so we might actually never find a tau here that will solve equation 2 up here. So instead, we formulate some kind of objective function or cost function here, and then we'll try to minimize that. And let's look at the objective function we have in equation 3 here. I've inserted a scalar a here to account for that the amplitude might change over time. And then I simply take the squared error here, and then the average across a lot of realizations of the signal. And this is the objective that we'll work with initially. If we then write this equation out here, then it's not hard to derive equation 4 from 3, where sigma x here, that is the expected value of x of n squared. So you can see here that in the 3 terms of equation 4 here, so this term here does not depend on tau, this term here does not depend on tau, only the last term here depends on tau. And this Rx of tau here, that's what we call the odds correlation function. And you can see that if we want to minimize our objective g here, what we have to do is that we have to maximize the odds correlation function. And so if we solve equation 5 down here, so we find tau that maximizes the odds correlation function, we have also find the tau that will minimize our objective up here in equation 4. And this is really the odds correlation method for estimating the fundamental frequency. So we try out all kinds of taus here within some range that we're interested in, and then find the tau here that maximizes. the autocorrelation function. In practice, we cannot, or in practice, the way we evaluate this expectation operator here is that we assume that we have a number of data points, and then we simply compute the average like this. And you can see here that if we increase tau, so we increase the period, then we will have fewer and fewer data points in our average here. Okay, so here the bottom 3 points on the slide here, they list how you would implement this autocorrelation method. So first, you shift the data by tau sample, where tau here is a candidate period that you take from your range. Then you trim the ends of xn minus tau, so they all the samples overlap, and then finally compute the average. So let's look at this graphically. So here's an example where in the top figure here we have 400 data points, and then we have shifted these data points by 45 samples, and then you get the middle figure here. Then we should trim the ends, and what we do here is that we cut away this part here and also this part here, because they don't overlap. And then the rest of the samples that will overlap, we just multiply them together. Then we get the blue curve here in the bottom figure, and then we compute the average of all these samples, and that's the red line here. Of course, it's just a scalar, but I've written it here as a constant, or drawn it here as a constant. And this is how it looks for another tau, so for 169. And yeah, again, we trim the ends here and here, so we can see we have even fewer samples now. And then the product is the blue one down here in the figure in the bottom, and then again I've computed the mean. And we do this for all the taus, all the candidate taus, and then we end up with the top figure here. So you can see that here our candidate taus runs from 50 and up to 220. So this will be tau mean, and this will be tau max. And then we just shift it by one sample at a time. That's the minimum shift we can allow for, and we get the objective function, or the autocorrelation function here in the top figure. We can also convert this to frequencies instead of time shifts, and then we get the figure down here. So again, the tau range will now be a frequency range, so this will be f mean and f max. So from 200 Hz to 1000 Hz. You can also see here that the distance between two frequency points for a high frequency is bigger than it is for low frequency points down here. And the reason is that we have a uniform distance between the points here in the tau domain, or whatever we want to call it, and here in the frequency domain, this is no longer uniform. And this is an inherent problem of this autocorrelation method, that the resolution here is limited by the sampling grid. So many methods you find out there based on your autocorrelation principle, they will include some kind of interpolation to get a subsample estimation, fundamental frequency estimation accuracy. But I'll not go into this this year. Okay, so this was the first method. Now let us talk about the COM filtering method, and that's actually very closely related to the autocorrelation method. So now we define the objective in a slightly different way. So instead of, recall that in the autocorrelation method, our objective was like this. So now we just explicitly replace this expectation operator here by an average. And the reason why this method here is called the COM filtering method is that we can interpret this as you filter your signal through a filter with this transfer function here, and then you'll get the error out. And you will try to find the tau here that will minimize the power of the output. And a comb filter, the name comes from the frequency response of this, that will look like comb flow, like this. And I'll show you a picture of this later that is better than my drawing here. So we still have this a parameter here, a scalar here, but we can find an optimal value for that. So first we fix tau, and then we solve the problem we find the a here that minimizes our objective. That's given by the expression in 9. Then we put this back into the objective, and then we have an estimator that only depends on tau. And that's given by the expression here in 10. And yeah, it might look a bit complicated, but it's fairly easy to implement. This is simply the power of the trimmed input signal. This is the power of this trimmed and shifted signal, and then this is the autocorrelation function. So you can see that it's fairly closely related to the autocorrelation method. So let's look at an example. So here is our time domain signal, and then this is the periodogram of our time domain signal, and then this is then the comb filter here, and you can see that here we have estimated the tau that will minimize the power of the error, and that happens when we place, so the comb filter here will place nulls where we have the energy in the input signal. And if you try out a lot of different taus, then you will get that the output energy is listed here on the y-axis, and you have the frequency here on the x-axis. And you can see that here, around 260 Hertz, this is the frequency where you minimize the output energy. So this is our estimate of the fundamental frequency. You can also see that you have another peak here, which has nearly the same value as the true fundamental frequency here. So if this is omega 0 hat, then this is omega 0 hat divided by 2. So if this is 260 Hertz, this is only 130 Hertz. And this illustrates a very common problem for pitch estimation or fundamental frequency estimation, and that is that of pitch halving or octave errors. And the reason why you get this value that is nearly as close as this value here is that if you if you double the period, then you get twice as many combs here. And you can see that we still filter out the energy here in the input signal, but you have additional nulls here, and you could triple the period, so the candidate period of, and then you would get something that will still cancel out the energy of the input signal. So that's the problem, not only for the comb filtering method, but basically for all fundamental frequency estimation methods. And I'll return to that a bit later when I talk about the nonlinear least squares method. Okay, so let's go to the nonlinear least squares method now. That works off a sort of different principle. So the way that we can understand it is that first let's look at this is 20 milliseconds of a speech signal, and you can see this is approximately periodic. And such a periodic signal, you can actually decompose that into a number of components. So here you have the first component. This is a simple sinusoid, so we could write it as an amplitude and a cosine, and then we have a frequency omega 0, n plus, and then a phase here. The second component, that's also a simple sinusoid, so we can write that as a2 cosine, and then omega 0 n plus, and then a phase here. But we should write a 2 here because the relationship between the frequency here and here is that this has twice the frequency as this one here. And this holds for every periodic signal, that the frequencies, they are related. All the frequencies of these components here are related to this fundamental frequency, omega 0. So the frequency of this one down here, the third component, will be 3 times omega 0. And this E of n here, that's sort of the rest. So you can see that it looks like noise, but it might not be noise, it might just be model inaccuracies. And if we just set the noise equal to 0, then you can see up here that we get a fairly good approximation of our speech signal here using only 3 components. What we basically did on the previous slide was that we formulated a mathematical model for our periodic signal. And this is stated here in equation 11, so you can see that any periodic signal, S of n here, that can be written as a sum of these harmonic components. And each harmonic component is a simple sinusoid, where we have an amplitude, we have a frequency, and we have a phase here. And the important thing about these periodic signals is that the frequencies are all related to each other. So we have a fundamental frequency, which is this one here, and then all the other frequencies are an integer multiple of this fundamental frequency. L here is the total number of harmonic components that we have. And this is nearly always unknown, and we have to do something about finding the right one in order to avoid problems with pitch halving or octave errors. So model comparison is really, really important if we want to exploit the mathematical model here in a fundamental frequency estimation. But I'll return to that later. So just one brief slide on least squares. So in least squares, we have some kind of data generating process here that will produce x of n, so what we have here. And then we formulate some kind of signal model for the data that we observe. And I'll call this for Sn, theta, so I included theta here just to make it explicit that the signal model here depends on some model parameters. And then we subtract the signal model from the data that we observe, and then we get the error here. And then the least squares principle is to minimize the squared error here, or find the parameters theta here that will minimize the squared error. So in this case, for the periodic signal here, we have the least squares error here, which is the difference between our periodic signal, so the one we observed, and our mathematical model for our periodic signal. And the mathematical model is stated here in equation 13, and the model parameters are stated here in equation 14. And now the way we then find the fundamental frequency or the other parameters is that we try out different values until we find a theta here that will minimize the square error. So that's the principle of least squares, and this is really stated here. So we try out different thetas here so that the objective will be minimized, and the objective here is, so we square all the errors and sum them here. Unfortunately, it's not trivial to solve this problem because the fundamental frequency is a nonlinear parameter. We can formulate the problem so that the amplitudes and the phases, they can easily be found, but the fundamental frequency is quite difficult. And this is the main reason why nonlinear least squares has not been used, because it has some very desirable properties in terms of estimation accuracy, but it's incredibly slow. So what people have done is they have often used an approximate nonlinear least squares method called harmonic summation. And this is what we are going to talk about now. So the harmonic summation method, that's actually a quite old method, and originally it was not based on least squares, but it can be interpreted as an approximate least squares, nonlinear least squares estimator. So the way that we can derive it is that so remember that this, what we have here, that's the least squares objective. And if we let n go to infinity, then from Parseval's theorem we can write it in the objective here in the frequency domain, as we have here. And then you can work out that the error here in the frequency domain is the data in the frequency domain minus, and this is how a sum of cosines looks in the frequency domain. And the alpha L we have here, this is a complex scalar that depends on the amplitude here and the phase here. And you can see that alpha here is a linear parameter, so we can in fact estimate it, and you get a very simple expression for alpha here. Then, as we have done before, we just plug alpha here back in to the error here, and this will give us the objective we have in equation 21. And you can see here that only the last term here depends on the fundamental frequency which we're interested in. So if we can maximize the last term here, then we have minimized the least squares error up here when n is large. So the expression we have in equation 22 is an approximate nonlinear least squares method, and it's called the harmonic summation method for historical reasons. And you can see here that x, that's the discrete time Fourier transform of our input signal. So if we only have a finite amount of data, then we'll just take the DFT of our input signal here, and then we'll take out certain spectral lines in the DFT. So we can compute this, even though this is a non-convex cost function, we can compute this cost function here on a grid very efficiently using an FFT algorithm. So the harmonic summation method is much faster than the exact nonlinear least squares method. And this is why, and it inherits many of the desirable properties of the nonlinear least squares methods. So the harmonic summation method here is often used instead of the least squares method. So some remarks here. This was what I was saying before. So the harmonic summation method can be computed very efficiently using a single FFT. And it's an approximate nonlinear least squares method. The harmonic summation method works basically as well as the nonlinear least squares method, except in a few cases. So one of the few cases is that when the fundamental frequency is low, then it doesn't work. It basically breaks down, and you can see why on the figure here we have in the bottom. The figure here shows the objective function of the harmonic summation method and the nonlinear least squares method. And you can see that when the fundamental frequency is high enough, so let's say it's roughly around here, 2 cycles per segment, so we have 2 periods, or at least 2 periods of the signal in the segment that we analyze, then they are basically equivalent. But if we have fewer than 2 cycles per segment in our data, then you can see that they are no longer equivalent. For the data here, the true fundamental frequency was 1 divided by it was 1 period in the segment, and you can see that the maximum here for the NLS method, that's the correct maximum, but for the harmonic summation method we get a wrong estimate here because the fundamental frequency is low. So whenever you use the harmonic summation method, you should never accept a candidate fundamental frequency that is less than, I would say, 2 cycles per segment, because then you might get these spurious estimates. Okay, so this was I haven't covered all fundamental frequency estimation methods because there exist hundreds out there, but many of them are variations of these methods I presented here. So I'll give you just a brief comparison here, and this should really work as a motivation for why we want to look more into the nonlinear least squares method. So to summarize, I would call the autocorrelation method and the comp filtering method for correlation based methods, and they basically work on the principle that I sketched here. So if you shift your signal with some time lag tau here, then the signal should equal itself. So that's the underlying principle of both of these methods. This is a very intuitive and simple principle. It's easy to find an estimate, it's fast to compute an estimate of tau here, and we don't have to compute the model order. That's really a big plus of this method here. But they don't work for low fundamental frequencies. We have found they are very sensitive to noise, and also we need some kind of interpolation if we want to do fractional delay estimation. And so fundamental frequencies, they are continuous in nature, right? So if we should be we should model nature as it is, our estimator should be able to produce estimates on a continuum, not on a grid. And if we don't do anything here, then we will only be able to compute frequencies on a grid. That might be accurate enough for some applications, but not for all applications. The other main group of methods, I'll label this group as parametric. So these are all based on a signal model, so the one here in 2024, and they typically have a very high estimation accuracy if the data is indeed periodic. If the data is not periodic, then the model is not very accurate and you might get over-optimistic results. But if the data is periodic, you can get very accurate estimates. They work well even in noisy conditions, and I will show that later. They can work for low fundamental frequencies, so NLS is a prime example of that. One downside is that we have to estimate this model order L here, which is typically unknown, and also that the computational complexity is typically higher than for the correlation-based method. Harmonic summation, that I will say that is basically as fast as these correlation-based methods, but nonlinear least squares is way slower. So let's look at an example here where we compare some of the methods. So we have 200 data points, we have 10 harmonics, and then we have 10,000 Monte Carlo runs, where we in each run randomize the phases, and we have constant amplitudes. And the signal to noise ratio is 15 dB, and the noise is wide and Gaussian. And what you can see here on the x-axis is the frequency we have used, and on the y-axis the root mean squared error between the true fundamental frequency and the estimated fundamental frequency. And the line you see here is the asymptotic Kremmer-Rao lower bound. If you're not familiar with the Kremmer-Rao lower bound, think about it as this is the best you can do. So you cannot invent an estimator that will go below this bound here, unless it's biased, of course. But for unbiased estimator, this is a lower bound. So this is NLS. So you can see that when the fundamental frequency is very low, it's quite far from the bound, but as the frequency increases here, it will go closer and closer to the bound. And it's actually not a surprise that in this region here, that it's far from the bound, because the asymptotic Kremmer-Rao bound is way too optimistic down here. In order to, if we could have computed the exact bound here, but the problem is that would depend on the exact realization of the phases, so we couldn't randomize it. So therefore we instead computed the asymptotic chromolar bound here, because that does not depend on the phases up here, only on the amplitudes, and that also explains why we have constant amplitudes. So this is then the harmonic summation method, and you can see, as we have discussed before, it doesn't work as well for a low fundamental frequency. It starts breaking down here around, I would say, 1.5 cycles per second. Above this point here, it's basically as accurate as the nonlinear least squares method, but below it, it's much more inaccurate. And here is a correlation-based method called yin. I don't know how many people actually uses yin anymore. It's more than 10 years old, but I think it's the most cited fundamental frequency estimator out there. So therefore we have included it here for comparison. And you can see that it also doesn't work very well for low fundamental frequency, and actually there's also a constant gap to this Krim-Rao bound, so it's actually a suboptimal estimator. Yeah, so now let's look at another case. So where we have the SNR is 0 dB, and you can see that compared to the previous case, the Krim-Rao lower bound, so you should look here on the horizontal line here, it goes up, and that tells you that the problem is more difficult because our signal to noise ratio here is lower. Everything else is exactly the same. The only thing we have changed here is the signal to noise ratio. So now let's try to look at the results. For this case here, you can see NLS basically behaves in the same way as before. The same thing can be said about harmonic summation. Well, there's one thing that has changed, and that is that it now starts breaking down before. So now it's 1.9 cycles per segment or so that it becomes as good as NLS. So above 1.9 cycles per segment, it is as good as NLS. What about yin? Well, yin completely breaks down in noisy conditions, and that goes back to a point I had a few slides ago, that these correlation-based methods, they are not very robust to noise, and you see that here. They break down in noisy conditions. Yeah. Good. So this was a background on fundamental frequency estimation, and the main conclusions are that yin here, as yin should represent, so basically most of the autocorrelation-based methods out there, that yin is suboptimal and it breaks down in noise condition. That's what we have found in general for these correlation-based methods. Of course, you can add things on top of them to smoothen out the estimates between segments. That will correct a lot of things, but you can also do that for NLS and harmonic summation. So this comparison here is only for the case where you have a segment of data. Yeah. So when the fundamental frequency is not low, harmonic summation is practically as good as the nonlinear least squares method. And since harmonic summation is much faster than NLS, then people use harmonic summation here instead of NLS. However, when the fundamental frequency is low, it's much more accurate than everything else out there. So this is really the main reason for using NLS. If you want a very good time frequency resolution, so you can allow to analyze very short segments of data, then you should use NLS. You cannot get the same time frequency resolution using harmonic summation, because you would have to use longer segments so that you are sure that you would have at least 2 periods in your segment. Unless you can go below 1, I would say. So not a lot below 1 cycle per segment, but you could go below 1 and still get good results. And this brings us to the contribution of this work, and that is that we have developed an algorithm for the NLS method that brings the order of complexity down to harmonic summation. In terms of seconds or computation time, it's not as fast. It's there's around a factor of 7 to 10 or so between them, but if you look just at the order of complexity, we have brought the NLS algorithm down. So it's now, I would say, a viable alternative to harmonic summation. So let's look at how we did that. So, but before I will talk about how we did it, I need to set up the estimator, the NLS estimator in vector form. I haven't really discussed the NLS estimator yet, but I will do that now. Then I will talk about how people normally would implement NLS, and then our fast method. So this is equation 25 here is the signal model in a slightly different form than what we have seen before. So before you saw the polar form of the signal model, so AL here and then cosine L omega 0 n plus a phase here. But you can write the polar form into the rectangular form here if you define AL as AL cosine to phi L and BL equal to AL sine to phi L. Then you get the expression here in 25, and the reason that we have gone for this rectangular form is that we would like these to be linear, so that we can easily marginalize them out from the optimization problem that we will look at later, so that we only have one unknown nonlinear parameter, which is omega 0 here. Another thing we have changed is that we haven't really decided how we would select the first time index. So before it was 0, but now we have left that open, so it could be anything, and it actually plays an important role later, because you can, if you select it in a so as n minus 1 divided by 2, then it will actually speed up the algorithm. It might sound a bit strange, but the objective, the value of the objective, will not depend on how we select the start index, but the algorithm will be significantly faster if we select it in this way here. So, but I'll return to this point later on and why that is. So equation 25, we can also write that in a vector form. So this is the same as, so this is written in equation 26. And the definitions of the matrices and vectors are down here. So set here will contain all the cosine. So these are all column vectors, and also all the sine column vectors, which are defined down here. And then alpha here, so the linear parameters, consist of these A's and B's. So you can see that if we knew omega 0, this will just be a linear signal model in alpha L. Yeah. So the least squares error we can also write then in a vector form. So this was the form you saw before. In vector form, it will just be this inner product between of this error vector. And then we can just insert the expression of the error vector here, and we get what we have in 27. And if we then assume omega 0 here known, then we can easily solve this for, or we can easily optimize this for the linear parameters, and we get this least squares estimate of the linear parameters. Then we plug this back into the objective here in equation 27 and rewrite this a bit, and then we can see that if we maximize the expression we have in equation 29, we can see that the fundamental frequency that maximizes the expression in 29, that will also minimize the least squares error. And this estimator here is not new. It has been known for at least 25 years, but so far no fast implementation has been known. Yeah, so let me go on and describe now how you would normally implement this NNS algorithm and why it's very costly. So the way you would compute the fundamental frequency, nonlinear least squares fundamental frequency estimate, would be in the following. So first, you would evaluate this cost function here. This is non-convex, as you can see in the figure up here. So you have to evaluate this on a grid. So we evaluate this on a grid here, and we have to do this for all candidate fundamental frequency. So assume that we don't know the fundamental frequency, but we know that it is below L max here. Then we have to find an estimate of the fundamental frequency on this, and now it's an F point grid. And we have to find an estimate on this grid for all candidate model orders. So this is the first step. The second step is that we can then refine these estimates. So assume that our grid-based estimate will produce an estimate here, for example, and the neighboring points are here and here. Then the refinement procedure will be a simple line search within this interval here. That will hopefully bring us up here. And yeah, the fundamental question is, what should the width be of this grid here? Because if we select a very fine grid, equation 30 here will be very costly to compute. But if we select the grid too coarse, we might miss the peak, right? So actually, it was a poor selection here, because we should have ended up here to find the global maximum. But this was just an illustration of how you would get from a local grid estimate to the refined estimate. And then the final step is that we have to do model comparison. So we have now found the grid estimates for all the candidate model orders, and then we can add a penalty term to the log likelihood, and that will sort of penalize model complexity. And then we can find the model order that will, so we can estimate the model order, and the model corresponding to this model order, I'll go a bit back. We can estimate the model order, or that's the same as estimating the signal model that we think is the one explaining the data, and we then look at, okay, what was the fundamental frequency estimate when we use the signal model, and then that's our final fundamental frequency estimate. Yeah, so in equation 31 I've again written this nonlinear least squares estimator, and now in equation 32 I've written the harmonic summation estimator. This is in a different form than what you have seen before, and the reason that I've included here is that you can see that how closely 31 and 32 are to each other. So if I just removed this part here, then I would actually end up with the harmonic summation method. And if you look at this inverse here, then you can see that that will converge to something like this as n grows. So when n is big enough, then removing this part here from 31 is actually a fairly good approximation, and that explains why harmonic summation behaves as good as NLS in some cases. The inverse here in 31 is also what causes the big computational complexity. I've written here in the bottom of the slide that if you just implement 31 here as it is stated, then the complexity here will be f log f. So that is the complexity of evaluating this, plus, and then f and L to L cubed max. This cube part comes from the inverse here, and f L max comes from the fact that we have to compute this for all the candidate fundamental frequencies. In 32, since we don't have to compute this inverse, the complexity goes down. And our contribution here, I've said it before, that we get the order of complexity down of the NLS method to the same as the order of complexity for the harmonic summation method. So that means that we get rid of this cubed part here. And I'll return to, so let's look into how we do that. And this is what we call the fast NLS algorithm. So here is the objective of the NLS method, 33. And if you look at the part here I've highlighted in red, what that says is that if we should evaluate this cost function here efficiently, we should be able to solve a linear system looking like this efficiently, because the solution to this system is what we have here. If you then look at the parts here in red, they can be evaluated efficiently using a single FG. This is the same as in harmonic summation. If you look at the coefficient matrix, the coefficient matrix is the one we have here, that has a block triplet plus Hankel structure. So this TL matrix here, that's a triplet matrix, and this HL matrix here, that's a Hankel matrix. The same, these are also triplet matrices, and this is also a Hankel matrix. Okay, so I've said this before, but this cost function here in 33 does not depend on the start index. And if we then select the start index as I told you before, as the symmetric choice here, then it turns out that this TL tilde and HL tilde, they will be the zero matrix. That means that this equation up here, instead of being a block triplet plus Hankel matrix, it will become two scalar triplet plus Hankel linear systems. Yeah, and here this part here, I just call this for W. So yeah. So so remember the first point was that we needed to solve this one up here efficiently, and now we have basically reduced that problem to that we need to solve a triplet plus Hankel system efficiently. So if we can solve this one efficiently, we can also solve this one efficiently, and we can solve this one up here efficiently. Okay, so let's look at how we solve such a triplet plus Hankel system here efficiently. There exist a lot of methods in the literature that can do that for you, that will reduce the complexity from L cubed to L squared. If you look closely at this, then you will also see there's sort of a recursive structure in the problem. So the solutions to all upper left subsystems is a solution to a lower order. So that means that if we just solve the problem for the biggest candidate model order, so L max here, using a recursive triplet plus Hankel algorithm, so it basically works in a similar way to the Levinson-Durbin algorithm, then we will get the solutions to all the problems for lower order for free in the process. So we will not go only from L cubed to L squared. We will go, so sorry, I was too quick there. So it means that when we go from the model order L minus 1 to L, then the complexity is only linear in L to solve this triplet plus Hankel problem there, and therefore this will bring the complexity from L cubed to just L to the power of 1 here, and so we can conclude that the total complexity of solving the problem that we had on the previous slide is solving the linear system is just the same as that for harmonic summation. And I know that it might be a bit hard to follow all these steps here, but I really encourage you to read the paper if you're interested, because there we have all the details. These are just the highlights, really. Okay, so let's look a bit more about on this triplet plus Hankel solver. So we have used an algorithm from Gober and Koltrakt from 1989, and one nice feature about this is that it consists of a data independent step and a data dependent step. So in the data independent step, we simply solve a problem like the one we have in equation 40. So you can see this doesn't depend on the data here, so we can compute this offline before we compute the data, and then we only have to compute the data dependent step for every new data point, and that will reduce the complexity even further. Okay, and this also brings us to a MATLAB implementation that you can download of this fast NLS method, and here is just an example of how you would use it. So it's an object. So first you have to define your estimator or construct your estimator object, and you do that by calling this fast if null NLS constructor here, and that you give them then the number of data points, the maximum number of harmonics, and the bounds for the fundamental frequency. There are also some optional parameters which I won't talk about now. And then you can, when you have constructed your estimator object, you can estimate the fundamental frequency. When you construct this, you also compute the data independent step. And then down here you then have the data dependent step. So you just plug in data and ask the object here to estimate the fundamental frequency. You can get the number of harmonics and also the linear parameters. Yeah, and I've only described here how I had this three-step procedure. So first we had to evaluate the cost function on the grid, then we could do refinement, and then model comparison. All these three steps there, they are included here. I won't describe the first step in this presentation. And maybe we should mention that the way we do model comparison is using numerical integration. And you can read this paper here if you're interested in the details about how we did that. The refinement is also included, and you can using a user-defined parameter. So here you could set the refinement that you wish. So if you want 1 Hertz tolerance of your final estimates, then you specify that here. I think the default is 10 to the power of -8 cycles per sample. So that's quite low. So it's a very accurate estimate you get out then. You can also, I've not described that here, but you can also include a DC term in the signal model, and then the algorithm here we have presented here, you need to modify it a bit, but you can include an optional parameter in the end here that will state that I want a DC in my model as well. But the default is that no DC is included. And finally, you can download this algorithm here from this by following this link here to our website. So let's look at a very small example of how you could do analysis of a speech signal using this method here. So first up here we load the speech signal. Then here we have the setup of the algorithm. You can see that we define the bounds on the fundamental frequency to be 80 to 400 because it's a speech signal that we're looking at here. We have a maximum of 15 harmonic components. Then here we construct the estimator object. And Then down here we do the analysis. So we have loaded in the speech signal and we look at segments of 25 milliseconds. And then we just, for every segment of data, we just call this data dependent step and ask it to estimate the fundamental frequency for this segment. Yeah, and the results look like this. So the speech signal is a female uttering "Why were you away, yeah, Roy?" I have an example of it here, so you can listen to it.
Why were you away a year, Roy?
Yeah, and this is a spectrogram of the signal, and then you can see the red dots down here. These are the estimates for each of these segments of the fundamental frequency. And you can see that it works fairly well here. When you download the code, there's also an audio example where we analyze a viola signal, I think it is. Yes, then let's look at some results. And the focus of this contribution has really to bring down the computational complexity. So this section here will also focus on how much did we in fact reduce the computation time. So in this setup here we have 200 samples that corresponds to 25 milliseconds at 8 kilohertz sample frequency. This is the number of grid points in our when we do our coarse grid-based estimate. So we have found that this works very well. You can also show why value of this works quite well. But yeah, look in the paper for a reference. And yeah, then these are evaluated on a T420 Lenovo laptop. And so what you see on the x-axis here is the maximum candidate model order, and on the y-axis you see the computation time. And the dotted line here is the real-time limit. So if we are below this dotted line here, that means that we can run the algorithm in real time. You can see this is the standard nonlinear least squares method. And that's far from real time. Here we have the fast NLS. So this is when we both run the data independent step and the data dependent step. And this is then, if we only run the data dependent step, you can see the complexity goes down. And you can also see that we can actually run this in real time for maximum candidate model order of up to 20. And this is then for the harmonic summation method. This is a bit faster than the NLS, even though they have the same order of complexity. And here is the relationship in computation time. So harmonic summation is roughly 500 times faster than standard NLS. And then you have that this faster NLS is roughly 150 times faster than the standard NLS. And you can see the difference between the faster NLS and harmonic summation here is only between 3 and 4 times here. Yeah, and here is a similar simulation, but instead of changing the model order, we now change the data length, and we have set the maximum candidate model order to 30, but otherwise the simulation setup is the same. And again, the dashed line here is the real-time limit. You can again see that the standard NLS is far from running in real time. Fast NLS, so the method where we compute both the data independent step and the data dependent step, is a lot faster, and even faster is the fast NLS, so this is only for the data dependent step. And then here we have harmonic summation, which is yeah, even faster still. Yeah, so finally an example from sound and vibration, where we analyze a washing machine signal, and I will also play that back to you. So hopefully you can hear modulations, and you can also sort of see it from the spectrogram. So the the source signal here was sampled at 44.1 kilohertz. We downsampled it by a factor of 10. Then we used 60 milliseconds windows and used a big overlap here. Maximum candidate model order was set to 15. And then here are the results of the estimated fundamental frequencies, and you can also see here, so in total we have 6 or 7 harmonic components, and you can see that the 7th harmonic here has a sort of on-off behavior, and the algorithm seems to actually accurately capture that. For the computation time, with this big overlap, it was 28 seconds, but if we went down to a 50% overlap, it would be 3.8 seconds, which we will be able to run in real time. So if we only show the estimated fundamental frequency, you can see some very fine details here, and you can clearly also see the modulation that you hopefully heard before. So the better model for this signal here would actually be a fundamental frequency within a fundamental frequency, because the fundamental frequency seems to be periodic. Often when you analyze a washing machine engine, you do it for order analysis, so you're really interested in seeing how does the power of the individual harmonics behave as a function of time. And here are then the estimated powers of the individual harmonics, and again you can see some very fine details here. So the 6th harmonic is clearly the strongest one, and then the 4th harmonic seems to be the next one, and yeah, and so on. Okay, so that brings us to a summary. So yeah, we have shown now that the NLS estimator works well for low SNR and or when the fundamental frequency is low. And whenever I say low fundamental frequency, what you should really understand here is that we can get a good time frequency resolution. So something that is a low frequency in hertz might be a high frequency if we consider long enough segments. On the other hand, a high frequency can actually be a low frequency if we consider short enough segments. But if we want a good time frequency resolution, then the NLS method is what is very good. NLS has been known for a long time, but we haven't really seen a complexity lower than this for the algorithm. But we have now lowered it to this, which is the same as the harmonic summation method, and this is roughly 60 to 150 times faster than the standard algorithm, and 10 times slower than harmonic summation. So I would say that in a lot of cases it makes sense to use the NLS method now instead of the harmonic summation method. So unless you know that you are not you don't need a very high time frequency resolution, then I think you should really consider NLS instead of harmonic summation. And finally, some resources. So I'm a part of the audio analysis lab, and you can find more about our lab on this website here. The first part of this talk was really based on a short lecture note by the head of the lab, Mads, which is also a co-author of this paper here. He has written a short tutorial on pitch estimation, which I encourage you to read if you're new to this field here. And yeah, and then again here, the MATLAB code, you can find the MATLAB code for the fast NLS method from here. And here are also some key references. So this one here describes the fast method I described in the last part of this talk. This part here describes model order selection, model order estimation. And finally, this one here is a very thorough book on fundamental frequency estimation using parametric methods. So if you're interested in this topic here, I'll encourage you to have a look at this book. Okay, so this ends the presentation.